Few questions hold greater importance in science than how it all began. What did the beginning of the universe look like? Why did it happen in the first place? And although we are a long way off from having a complete answer, scientists have learned enough that a theory has been conceived: the Big Bang. By examining stars and the spectrographic data given off by matter when light passes through it, we have assembled the jigsaw pieces of the Big Bang and have begun to form a picture of those first explosive moments. But here's the thing about jigsaws. Sometimes you find a piece that just doesn't fit. At that moment, you realize with a sinking heart, you've made a mistake somewhere along the way, and you have no idea where. Is this what's happening to the Big Bang Theory? Or are we looking at our puzzle piece the wrong way round? It all comes down to an element we use every day. In medicines, alloys, and most importantly, the batteries in our phones. One that is strangely missing from the universe, at least in the amounts we would expect. So here's the big question: where is all the lithium? I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we examine the lithium discrepancy, a mystery that continues to confound scientists to this day and might force us to reevaluate our models if we ever hope to answer the question of where we came from. But before we dive into any of that, here's something that not only helps me sleep, but also helps support the channel. Manta sleep masks are designed to create a blackout effect, making sure you receive the best sleep possible. They come in a range of different variants, from their original sleep mask to their Pro for comfort and breathability. However, if you love listening to these podcasts, there's also a sound version which will help you fall straight to sleep. Use my link in the description and the code Astrum at checkout to receive 10% off your next order. To begin with, let's cover some of the basics about lithium. Lithium is a relatively simple element. It's one of the alkali metals, and for a metal is surprisingly soft, capable of being cut with just an ordinary steel knife. You might have seen it used in science experiments in school, as it reacts quite satisfyingly when mixed with water, producing lithium hydroxide and hydrogen gas. More commonly, it's used in phone batteries, laptop batteries, and in other electronic devices due to its high electrochemical potential. But the feature of lithium that makes it so important for our discussion is its internal structure. It's made with just 3 protons in the nucleus, meaning it's one of only a handful of very lightweight elements that could be created in the early moments of the universe. But it's the expected presence of lithium in the universe's beginning that causes our problem with the Big Bang model. So what do we think was going on back then? How exactly does lithium prove it's wrong? Well, the universe's origin is murky to us. After the discovery in the 1920s that our universe was expanding, a Belgian cosmologist, Georges Lemaitre, theorized that if the universe was getting larger and cooler, it used to be smaller and hotter, with all that energy being squeezed into a smaller and smaller area. The logical conclusion to this was that if you rewound the universe back to its very beginning, all of the universe's energy would exist in a single point in space. This singularity would be infinitely hot and dense, which makes sense. Based on that heat, this idea is known as the hot Big Bang model. But it's this infinity that causes the murkiness to creep in. Einstein's theory of relativity can be used to predict the motions of objects under the effects of gravity, but no equation tends to function when you start adding infinity into the mix. Hence, at the very first moment of the universe's origin, we don't have the equations to describe very well what was going on, or what caused the universe to start expanding. And with an infinitely hot and dense singularity, There's no way of knowing what might have gone on before it. Any evidence or signals from before that time would have been met with the hottest incinerator the universe has ever created. It happened somehow. That's all we can say for sure. At this point, there would be no lithium. The very start of the universe would have been simply too hot. After that though, even just 1 second after the universe begins to expand, the picture becomes much clearer. 1 second after the universe's expansion began, the temperature of the universe dropped down to a mere 10 billion degrees Celsius, which is actually only 1,000 times the temperature at the center of our sun. This was still hot enough that matter couldn't form yet. The strong force, the fundamental force that holds together the nuclei of atoms, would have been overwhelmed by this intense energy. So everything would have existed in the form of radiation instead, the remnants of which we can still see today in the cosmic background radiation. Discovering this became one of the proofs that scientists are onto something with this model. The universe didn't remain as just radiation for long. Just 99 seconds later, it would have cooled to 1 billion degrees Celsius, and the strong force would have kicked in. The universe's first protons by then had started forming and began binding with neutrons, creating hydrogen and the 1 proton, 1 neutron isotope of hydrogen known as deuterium. Hydrogen and its isotopes, or versions of hydrogen that had the same number of protons but more or less neutrons, were the most common element in the universe. But hydrogen wasn't the only one. Everything was still filled with so much energy that the hydrogen protons frequently smashed into each other, underwent nuclear fusion, and soon created the larger, more complex element helium with 2 protons. Once you run the equations, in the primeval universe, matter was nearly 76% hydrogen and nearly 24% helium. But sometimes, very rarely, another proton would merge with the other 2 and would form isotopes of lithium, bringing the number of protons up to 3 in these atoms. By mass, this made up only 0.0000007% of matter in the early universe. But here is where the mystery comes in. By examining the spectroscopic data from stars, or by evaluating that same light as it passes through clouds of matter, we can evaluate the distributions of elements in the universe today. And what we see roughly matches this prediction. Our own sun is, by mass, 71% hydrogen, 27% helium, and 2% other heavy elements. Which makes sense, as the sun would have had time to undergo more nuclear fusion in its lifetime, slightly altering the ratios of these elements. These ratios are mirrored throughout the universe as a whole, another strong proof that the hot Big Bang model and our equations are right, and that the universe did evolve in this way. And yet, our predictions about lithium are wrong. Although the prediction for the amount of lithium in the early universe is really low, the prediction is actually still too high compared to what we see. 3 times too high. Or to put it another way, as we study the spectroscopy of primordial stars, the further away the star, the earlier in time the light would have left it, we don't see anywhere near the amount of lithium we ought to be seeing if our prediction was correct. There are further mysteries surrounding lithium. Lithium-7 is the isotope that we tend to see in the early universe. This means that a lithium atom has 3 protons and 4 neutrons in its nucleus. But there is another isotope of lithium, known as lithium-6, with 1 fewer neutron, that is meant to be much less stable and much less common than its counterpart, supposedly making up only 2 out of every 100,000 lithium nuclei. While the amount of lithium in the universe is too low, the ratio of lithium-6 to lithium-7 is much too high. Lithium-6 is a staggering 1,000 times more prevalent in the early universe than it should be. So, what does this mean for the hot Big Bang model? When faced with something like this, one of two things must be true. Either our observations are wrong, or our models are wrong. Let's consider each possibility. It's difficult to throw out the hot Big Bang model completely. Nothing else does as good a job at explaining the existence of the cosmic background radiation, or the amounts of hydrogen and helium that we see in our universe. The quantities of those elements check out almost exactly with the hot Big Bang's predictions, which seems to be too perfect to be a coincidence. That said, scientists are becoming less certain about the model as it stands. Stephen Hawking, who was once one of the leading advocates of the idea that our universe began with a singularity, later went off the idea. In his book, A Brief History of Time, he stated, "Roger Penrose's and my work became generally accepted, and nowadays nearly everyone assumes that the universe started with a Big Bang singularity. It is perhaps ironic that, having changed my mind, I am now trying to convince other physicists that there was in fact no singularity at the beginning of the universe. As we shall see later, it can disappear once quantum effects are taken into account." Those quantum effects are too complicated to go into for this podcast, and this doesn't necessarily solve the lithium problem even if true, but it does highlight that the origin of the universe is an evolving branch of physics and cosmology, where the full explanation of it has not yet been found. Perhaps our models will one day adjust in such a way that the lithium problem falls away, even as the broad brushstrokes of the theory remain in place, letting the jigsaw piece of the lithium numbers fit nicely with hydrogen and helium. The other option is that there is something wrong with our observations, and there may well be some grounds to this. Because of the small amounts of lithium being discussed, it is quite difficult to see the exact amounts of it that exist in the interstellar medium and to look far back enough. The only way to probe the interstellar medium's makeup is to shine a light through it and then see which lines in your spectrograph get blocked out. This can tell scientists what elements might make up a particular nebula or dust cloud, but this gets harder and harder to do the further away the target is. Eventually, it becomes completely impossible to get an exact estimate. Instead, scientists are left looking at the spectrographs of primordial stars, which are not necessarily representative of the universe as a whole at that time. A star is a special case. Something going on inside there might be altering the amount of lithium present within, converting the lithium into something else, while boosting the amount of lithium-6, although it's difficult to guess what that process might be. If our observations could improve, and we could better measure the amount of lithium in the early universe as a whole, perhaps the numbers would come back into line on their own. Maybe the lithium problem never existed in the first place. Ultimately, no answer to how the universe came to be will ever be complete until all the available data matches the theory's predictions, whether that's lithium or other problematic elements in the universe like the overabundance of gold out there, which is another number currently not lining up. All these numbers have to be brought into line. There is still so much to learn about the universe's origins. I do find it incredible just how much we are able to learn and deduce about events that happened billions of years ago, back before matter itself had properly formed, using just our telescopes and our minds. That picture, the grand picture of how it all began, is waiting to be assembled. However the universe came to be, it is built on a foundation of an underlying order that allows us to unlock its principles, tease out its mysteries, and reconstruct the configuration of its individual pieces. One day, I am confident we will solve the lithium problem too. How can we resist when the answer to our ultimate origins awaits? Some questions are just too important to leave unanswered, and I, for one, Can't wait for the day this jigsaw piece is ultimately completed. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the lithium discrepancy. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.